Okay, so last time we had talked about the first part of chapter, or 15.3, and I think we had assigned up to 68 in the problem set at that point. Questions from homeworks at this point? Grace? 17. That was so fast, Leo.
Yeah.
Did you need an ID?
I don't know, just in case they do need it.
I'm sure that they want it. Okay. So for 17 through 28, they just want us to set up the equation. It says find the exponential function that satisfies the given conditions. So for each of these, I'm going to be using our population model that we talked about last time, or not last time, the time before last, a couple days ago, anyways. So remember that P naught is the initial value, so that's going to be 5. R is the rate of change, so in this case that's 17. And then our independent variable is T. So if we wanted to simplify this down, 1 plus 17 over 100 is 1.17, and that's it. We're just writing equations. Peyton?
Okay, so at 21, I kept doing what like 17 through 20 was doing.
Okay.
But then I was wrong. Like I'm so you do that one.
Oh, okay. Did you see the word decreasing?
Yeah, I guess. But
so what is that going to say about R?
is it?
It would make it negative. And that's probably the difference, right? So that would be like 0.974 when I simplify that. You know, all I'm doing, I'm just doing it in my head, but I'm doing 1 plus negative 2.6 divided by 100. And that's 0.74 or 974. Is that okay, Peyton?
Mm-hmm.
Was it you think it was the decrease piece that you just had missed? Or is that the wrong answer? Is that different than the answer in the back?
No, that was right.
Okay. You're just making some faces at me like I was. Is it my penmanship?
No, you're fine.
Okay.
Thank you.
I know that, like, I don't know. It's my penmanship. I understand. Anybody else with questions? Grace. 32. Okay, it says the half-life of a certain radioactive substance is 65 days. Suppose there's 3.5 grams initially. Express the amount of substance remaining as a function of time. And then when will there be less than 1 gram? Okay. So again, I'm going to be using the population model to do this. Initially, we're told we have 3.5 grams. And to get the R, the key here is the word half-life. That implies that R is negative 50% because the amount is being cut. So it's decreasing, so it's negative. And if I have a sale for half off, that's a 50% off sale, right? Just to try to put it in a language that's like, oh yeah, sure, of course, half is 50%. It's like, you know. So that's that. Now, here we have to be a little bit careful about our unit t. So it says a function of time t. So I'm going to choose for t to be in days. Okay with that? So it says to get one half-life, we need 65 days. So how much of a half-life can we do in 1 day? 1/65th, right? Does that make sense, Grace?
Wait, can you say?
Sure. So I'm just going to change some numbers to make it a little bit more obvious. So takes 100 seconds to do a job. What percent of that job can you do in 1 second? 1%, right? So like, or 1 out of 100, right? 1/100th of it. So like, how much can I do of a 65-day job in 1 day? 1/65th of it. So I'm going to change this to t over 65. So that's my answer for A. To do B, I'm going to put 1 in. And then use my calculator to get the rest of this. So I'm going to put 1 in that spot. And then we have 3.5 times 0.5 to the x divided by 65. Going to reset my window. So the x is my time. So take 65 days to cut it in half. So after 65 days, we'll be down to like 1.75. And then I cut in half again, I'll be under 1, right? So I'm going to do like 130. That's 2 half-lives. And I know certainly within 2 half-lives, I'll chop it down under 1. Does that make sense? Okay. And then for the y's, again, the minimum I can have is 0. Like eventually it'll all disappear. And we're starting at 3.5. I'm just going to use 5 as a round number to start. And then let's hit the graph. So there's my y equals 1 line. Here's my decay curve. There's my intersection I'm looking for. Just barely got it in there, but we got it in there. Intersect command, enter, enter, enter. So 117.5 days. Yeah, basically the exact same problem, just with different numbers. Yeah, of course. Peyton.
Did you do 60?
60? Sure. Oh, I didn't copy that far. Good job, Mr. Kulik. Hey, get off my back, man. It's Friday and it's not even 8 o'clock yet. All right, 60. Okay. So this says e to the ln of 1/5. What I'm going to go back and reference here, yesterday, is this property 4 that I've highlighted here in yellow. So this says b to the log base b of x is just x. So that's the property that I'm going to be using for this problem, because what is the base for the logarithm ln? It's not 10, it's e. Log with no subscript is log base 10, or it has base 10. ln is log base e. But the point of that is that this log, or this exponent base, matches that log base. So they just cancel, and I'm left with just 1/5. That's what that property 4 from last time would be telling us. Which is lovely. So easy. Okay. Anybody else? Cool beans, dudes. Let's pick up where we left off. In section 15.3. So, some more properties of logs. We have 4 more properties that we're going to talk about here today. The first one is called the product property. And this says that log base b of x times y is equal to log base b of x plus log base b of y. The quotient property, log base b of x divided by y is equal to log base b of x minus log base b of y. There's the power property. It says log base b of x to the a is going to be a times log base b of x The last one is called the change of base formula. It says log base b of x is equal to log base b of log base a of x divided by log base a of b. Because you did it last year. We did this last year. So at first glance, some of this stuff, while familiar because you did it last year, these rules seem non-intuitive, right? That multiplication inside the logarithm turns into addition outside of the logarithm. Right? That's what we're seeing here. Seems a little strange. That is, until you remember that logarithms are related to exponentials. So remember when we had like x to the a times x to the b, that gives me x to the a plus b, where you're seeing that multiplication between the exponentials turns into addition inside the exponent. You guys see that? So this product property of logarithms is just the logarithmic version of that property of exponents. Does that feel okay? So similarly here, remember for exponents, if we had x to the a divided by x to the b, that's x to the a minus b. Same idea. So division inside the logarithm turns into subtraction outside the logarithm. For exponents, we have division outside the exponents turns into subtraction in the exponent. And this last one is like the exponent of an exponent property. So remember that this is x to the a to the b is x to the a times b. So again, we're seeing that an exponent on the outside turns into multiplication on the inside. Here we have the exponent of the inside turning into multiplication on the outside. Does that feel okay? Now the change, oh boise, that jumped on me. The change of base formula here is not related to any of the, or directly related to any of the properties of exponents. Basically what this is just a way to translate a logarithm into a logarithm of any base that you want. This is not so useful to you guys now, but when I was in high school, this was super important formula because our table of logarithms were all base 10 or base e logarithms. So if I wanted to do log base 2 of something, I had to rewrite that as like a all base 10 or all base e logarithms so I could look up the values off my table. So, for example, if I wanted to do log base 2 of 6, back in the day I didn't have a calculator I could type this in. I would have to rewrite this as like log base 10 of 6 divided by log base 2 of 6. I go to my tables and I look up the value for this one and I look up the value for that one, and then that's the division that I can do on my 4-function calculator. Now you guys, this is much less important to you because you can type in log base 2 of 6 onto your calculator directly, right? We talked about that last time. How did we do that last time? Do you remember where that is? Yeah, press the math button, and then what are we looking for? Log base, which is down way at the bottom. And then we can just type it in the way it looks like on our sheet of paper. As opposed to Mr. Kulik, who had to do, log of 6 divided by log of 2. Look those values up separately, and then divide them. Gets to the same result. Everybody's cool?
So wait, super random question.
Yeah.
When did they start making calculators like this? What year?
Well, these, they had graphing calculators when I was in high school, but they were like nobody had them and nobody knew what to do with it.
Yeah.
So like they had, like the scientific calculator was probably about as good as you had, but not everybody even had one of those. Some of us just had like the 4-function, like add, subtract, multiply, divide calculator. And if that's what you had, you were learning logs by looking stuff up off a table or looking up your sine and cosine values up off a table. So, yeah, in a lifetime, right? By the time I was like upper high school, I had a scientific calculator where all these things were built in, so I didn't have to look these things up. But some people were still looking them up, even when I was in high school. Like you'd have these charts in the back of the book with the tables in them that you'd have to flip to and look it up. It was a hassle. Much easier. Okay. So there's 2 types of problems that we're going to be looking to do. There's going to be expand and compress, or sometimes condense would be the verb that we would use here. For expanding properties, or for expanding problems, we want to do quotient, product, and then power. unless we have like some parenthesis that would imply that we should do some more other order going on. But in general, that would be the way you'd want to do it. To compress, we're going to do the opposite order. So power, product, quotient. It's okay. So let's just run through a couple of examples. So let's say we have log base 3 of 4x. Start with something real easy. So what I'm doing is I'm first looking to see if I have any quotient properties going on. So I look inside my logarithm and look for any division. Is anything being divided? No. So no quotient property. Then I look for a product property. So if I look inside that logarithm, is there anything being multiplied? Well, yeah, right? 4 times x. So if I apply my product property, I would have log base 3 of 4 plus log base 3 of x. Then I would look down inside of each of these and look to see if there's any other quotient, product, or power properties going on in these. So if I look at log, let's look at the 4 first. Is there a quotient property going on? No. Is there a product property going on? Is there a power property going on? Can't I think of 4 as 2 squared? Uh-oh, Mr. Kulik. So it kind of is a power property going on with that one. So if I choose to use the power property on that, so Mr. Kulik, you're telling me sometimes you can hide a power property or a product property inside like just a number? Yeah, that's kind of crappy. Well, it'd be crappier if I didn't tell you about it, right? It's like, it's kind of tricky, but at least I'm showing you the trick before it's just like, get all these wrong because you didn't do all of it. Right?
So you can do that for every time you're looking for a power property.
If you have a perfect square, for sure, yeah. Or if that number was like 6, you could think about it as 2 times 3 and do a product property, right? But if it's a prime number, if that number was 3 instead, there's nothing more to do with that. All right. Let's go and look at the log base 3 of x now. Any quotient? Nah. Product? Nah. Power? Nah. So that's as good as we could do. Let's do another. Okay. So for expanding, we're looking inside the logarithm. First thing we look for is good, the quotient property. Do we see any division going on here? Yeah, man, it's a fraction. So if I apply the quotient property, I'll have the natural log of the numerator minus the natural log of the denominator. So let's look at the first logarithm that we have now. So we start over. Any quotient property you see in the natural log of the square root of x cubed minus 5? No. Product? No. Power? Look closely. The square root is a power. What power is the same thing as a square root? A half. A half. So remember the property that we're using was this one. Remember that? We talked about that the other day, or reminded us about that. So this is really, write it in blue or something. So I can use the power property to do that. Okay, let's go ahead and look at the 2x here. Quotient property. Now, product property. Yes. What's being multiplied? The 2 and the x. I'm looking at the 2x, Holmes, on the first line. So 2 times x, right? So I'm going to write that as 2x, or natural log 2 plus natural log x. Did I do that correctly? What do you guys think? Everything correct so far? You're suspicious because I'm asking this question in a way that would lead you to believe that there's something incorrect. No, it's not. No, unfortunately not. Mr. Kulik's made a mistake here. He did it intentionally because this is the most common mistake made on this kind of problem by students. Where's the mistake? Why is that wrong? It does need to be negative. Why? Because this whole thing was negative. So really what we should have is that everything that thing becomes needs to be negative. So when we distribute the negative through, we really should have this. Remember that trick. It will come up. What's your cue to look for on that trick? When you see a product property in the denominator. Okay? That's your cue to say that, oh boy, see, there's that tricky thing Mr. Kulik told me about. Easy to miss it, but I'm trying to remind you really hard right now that whenever we have a product in the denominator, we're going to have that tricky distributing the negative thing going on that we just highlighted. Okay? All right. Last chance. Do we see any more properties going on in any of these logarithms? So we're down at the bottom. We have 1/2 natural log x cubed minus 5 minus natural log 2 minus natural log x. Any more properties going on that you can see?
Did you say something for the power property? Third, or no?
Well, here's the problem. The answer is no, but here's the issue, is that this whole thing isn't to the third.
Oh,
Right? It's just one part of it is to the third. If I had like x minus 5 to the third, then we could use the power property. If it's just one part of it, nah. Or even if I still couldn't use the product or power property even if I had this. Still can't do it. Is that okay? It has to be the entire thing, not all the pieces, but the entire thing. So this is done. Let's do some condensing examples. Okay? And then that feels like probably a good place to stop. How's that sound to you guys?
cool.
Yeah. Okay. So for expanding, we're looking inside the logarithm for our properties. For compressing or condensing, we're going to look at what's going on outside the logarithm. Okay with that? So this is inside, this is outside. So the first thing we're looking for are power properties. If I go back and I look at a power property, what I'm looking for are coefficients, right? That's what's happening on outside the logarithm to cue me for a power property. So if I go back to my problem, do I see any power properties? Yes. I see a coefficient here and a coefficient there. Is that okay? All right. So if I apply my power property, that 3 is going to move to the exponent on the y, and that 2 is going to move to the exponent on the, oh, that was a 5, on the x. So far, so good? All right. Next thing we look for is product property. If I go back to the product property, what I'm looking on the outside is for addition. Yep. So do we see any product property going on? Sure, right here. So what do I write? I have log base 4 of xy cubed minus log base 5 of x squared. Last thing we'll look for is the quotient property. So if I go back up and look at my properties for quotient, I'm looking for subtraction on the outside. Do I see a quotient property here? No. It is subtraction, but why is it not a quotient property? The bases of my logarithm are not the same. One is base 4, the other is base 5. If you go back and you look at the property here, have to have the same base to do either quotient or product properties. Okay, it's sneaky trick, Mr. Kulik. Yeah, but I'm showing it to you guys. I'm showing it to you. If they were both base 5 or both base 4, then yes, we could do the quotient property. Since the bases are different here, we can't do anything more. This is where the problem would have to end. Okay. Let's do uno más. So what do we got here? 4 natural log A minus 3 natural log AB plus 2 natural log B, and then I'll do minus natural log C. All right. What's the first property I look for when I'm condensing? Power property. Do I see any power properties?
Yes.
Yes. How many do we see? 3, because I see 3 coefficients. Remember, when we're condensing, we're looking on the outside, not what's going on the insides. So when I apply that, I do this. I want to point out to you here, notice that the whole AB is cubed, not just writing AB with the cube at the end where it would imply only the B is being cubed and not the A. So everybody's okay with that? All right. Next up is product property. Do we see any product properties? What are we looking for on the outside with a product property? Addition and the same basis. So yes, we have one product property going on here. And I know they're the same base because everything is LNs, which are basey, right? Now, ooh, this is, all right. All right. So there is a one product property going on, but it's not going on between the natural log of AB cubed and the natural log of B squared. Mr. Kulik, what? It's going on between these two guys? Why? Why would it be going on between those ones? Those guys are both negative. They were the denominator of some quotient problem. They're not part of a product property. They're part of a quotient property. Do we see that now? So we have this. And actually, if you're clever, there is another product property going on. What? But everything says subtraction. Where's the other product property, Mr. Kulik? So if you look at the previous example, remember how we had to distribute that negative? We're kind of doing the opposite direction now. So instead of distributing that negative, I'm going to factor the negative. And I'm going to go ahead and expand those right as A cubed and B cubed. You guys see that? Mr. Kulak, this is a sneaky jerk of a problem. Well, this is kind of as hard as I would ever make one of these things right now. So just like allows me to talk about all these little like funny things that can happen before I unleash you to work on these on your own. Let's do like kind of the hardest possible version that we would see so I can talk about all these little like weird things that can happen. You know what I mean? So there's another product property, whoop, that was hiding there, Mr. Kulik. It just takes a minute to get the hang of it, guys. It'll be okay. It'll be okay. Is that okay now with what we've done? Last thing we look for is quotient. And what am I looking for on the outside for a quotient property? Subtraction, which is what I see there. So I'd have this, and if you wanted to, you could reduce inside there. And do that. So this looks like a good place to stop because that's kind of the end of 1513. That's the last main topic. Let's see. I don't want you to do 69 or 70. It's not within the scope of this class, so we're going to skip those guys. And we should use be able to do to 98 then. Yes. Of course. And
Up to 36.
correct. Yeah, up to 36 will be due this weekend. All this other stuff will be due next weekend.